Uh, our next chapter is nanotechnology. Nanotechnology is our next chapter. You have studied nanoscience and nanotechnology in your fourth year. Probably Dr. Faisal has taught you nanomaterials and nanotechnology. Now, for uh, for your uh, uh, for recovery or for your remembrance, I'll say some words on nanoscience or what is nano, just to be acquainted with these words. You have already Dr. Faisal already teached you this thing. Now, what is nano? What is nano? Actually, it is 1 billionth of a meter. What is 1 billion? 1 billion is about 100 crores. So nano means 1 billionth of a meter. That is 1 nanometer, which means dwarf. It is a Greek word which means dwarf. Dwarf means small. Small means there are আমরা বলি বামুন বামন কতগুলো লোক আছে না ছোট 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 দেখা যায় বামন লোক they are nano, they are dwarfs. Actually their names are dwarfs. So nano means dwarf. It is 1 billionth of a meter. So actually 1 nanometer is about 3 atoms long. If you place 3 atoms side by side, the length will be 1 nanometer. The length will be 1 nanometer. Now, what is nanotechnology? Nanotechnology means building something with that nanoparticles. That means particles of nanometer range, building something with the particles of nanometer range. That is called nanotechnology. Building and using materials, devices, and machines at the nanometer scale. You can build a machine in nanometer scale. So the technology that to build that machine is known as nanotechnology. Generally by nano, we mean 1 to 100 nanometers. By nano, we mean 1 to 100 nanometers. Say, for example, a particle which has a length of 50 nanometers, then we can call it nanometers. A particle which have a length of 100 nanometers, so we can call it nanoparticle. But if a particle has a length of 500 nanometer, then we will not call him a nanoparticle. So a particle with a length of 1 to 100 nanometer is known as a nanoparticle. And by this particle, the technology developed by this particle is known as nanotechnology. You can tell building and using materials. That means building of nanoparticle is also nanotechnology. How you can prepare a nanoparticle, that is also nanotechnology. And actually the chemists do work on that portion, how to build a nanoparticle. And the engineers, the physicists, they will do with that particle, with nanoparticle, they do various type of they prepare various types of machines and other things by the engineer. But with the chemist actually prepare that nanoparticle for them, prepare that nanoparticle for them. So building of nanoparticle is also nanotechnology, and using that nanoparticle is a nanotechnology. So we can build a nanoparticle of zinc sulfide, for example, or if we can build a nanoparticle of cadmium sulfide. So it is the work of chemists. It is chemists solely work on that building of a nanoparticle. It is the work of chemists. But what physicists or engineers do, they take that nanoparticle and they do, say, for example, a quantum dot with that nanoparticle. They prepare a quantum dot television with that nanoparticle. That is the work of engineers and other discipline peoples. Our work is to build that nanoparticle. So so what do you mean by nanoparticle? First, the nanoparticle means the particle with a length of 1 to 100 nanometers. And I told you another thing, that 1 nanometer means 3 atoms long, about 3 atoms long. Say, for example, we have a nanoparticle of, say, 50 nanometers. So in that particle, we'll get about 150 atoms. We'll get 150 atoms. So this is the nanotechnology, and this is the definition of nanotechnology and nanoparticles. So how small is a nanometer? If you see the beans, say the seed of the bean, seed of a bean, or a barboti. Huh? The seed of that barboti is like that. It is about 1 centimeter. If you divide it into 10 equal parts, you'll get a worm, worm like flea. It is of a millimeter. And if you divide it again 10 equal parts, then you will get your hair, human hair. That is 100 micrometer long. And if you divide a human hair to 100 equal parts, you will get the size of bacterium. A bacterium is of a micrometer, 1 micrometer. Now, a virus is about 100 times smaller than a 10 times smaller than a bacteria. Say, for example, coronavirus. Coronavirus is of the length of 100 nanometers. Now, a virus is you can call it a virus a nanoparticle. And if you divide a virus to 100 times, then you will get a nanometer scale. Say, for example, a molecule, a small molecule, or 3 atoms, that's like. So this is the nanometer. We cannot see a nanoparticle. So these are the things that are small, rather, that are small, not nano, that are small. In this side, in the left side, they are natural things, and in that side, they are man-made things. They are small. Say, for example, ATP of a man's cell. It is about 10 nanometer diameter. A DNA, the diameter of a DNA is about 2.5 nanometers. This are the red blood cell is 7 to 8 micrometer. And these are some man-made things. These are that are nano scaled. You see a computer chip. In 2008, it was 15 nanometer. Nowadays, it is about 10 nanometer or 5 to 6 nanometer. These are carbon nanotube. It is 1.3 nanometer in diameter, or this is fullerene. This is fullerene. It is about 1 nanometer in diameter. So these are some particles that have that are small, not the nano. So here we can see some beautiful nano structure. This is a quantum coral. This is called quantum coral, made of these are the irons. These are the irons. These are positioned like that, like a stadium, and the flat things are copper. These are ornamental thing, and this is a three-dimensional nanostructure got by controlled nucleation of silicon carbide nanowires. So these are some nanoparticles. These are silver nanoparticles. These are gold nanoparticles. These are some nanoparticles. Now, why we want nano? Why we want nano? Why small is good? Because first thing, because it is a small, it works faster. And as because it is a small, it is lighter. As because it is a small, it is lighter. A small thing is lighter. It must be lighter. And it can get into small spaces. It requires small, very small space to keep. And as because it is a small, you require a less amount of material to prepare it, so it will be cheaper. As because it is a small, it requires a small amount of raw materials to prepare it, so it is cheaper. And it is more energy efficient. Why it is more energy efficient? Because all the atoms works together. Because it is a small, all the atoms works. Hence, it is very much energy efficient. Less waste product. So as because it is a small, so waste is also small and uses less energy because it is a small and materials to produce. And the last one, which is the most important, it has different properties at a very small scale. When you go to the small scale, it will show different property than the bulk material. Say, for example, this is a bulk material. But if I take 2 to 3 atom from it or molecule from it, the property of that material will be different. So this is the main reason. Different properties at a very small scale. At a very small scale, the property will be different. For that, the small is good. For that, the small is good. So why small is good means why we use nanoparticles. These are the causes. You see, if your hard disk drive is small, you can use it in a laptop. Huh? But if your hard disk drive is thick like that, you have to use it in your desktop machine. So it can get hard disk drive can get into small spaces. It should be cheaper. It should be cheaper. Your desktop hard disk drive is
আগে মাস্টার্সের পরীক্ষা
আমজাদ কিছু বলছো?
না স্যার স্যার টিপ পড়ে গেছে
আচ্ছা। So it should be cheaper because you require less material to make that. You require less material to make that. So it should be cheaper. It should be cheaper. And it is more energy efficient. It is more energy efficient because there is no loss of energy for that material. Everybody works together. Everybody works together. So this is more energy efficient. We'll see about this later. And the most important one is it has different property. The nano material has different property than bulk materials. Now, what type of different property? This is some painting of ancient peoples. These are some paintings of ancient people. This painting is of gold, and this painting is of silver. Now you know the color of gold is yellow, yellowish, or the golden, which whatever we see. The color of the gold is yellow, but here you see you are getting the color of the gold is different color. You are getting the gold color, different color of the gold. You see, when the size of the gold is about 25 nanometer, then the color will be like that. And if the size of the gold is about 50 nanometer, then the color will be like that. And so as silver. So as silver. You see, these are the colors of silver. These are the colors of silver. When the size of the silver reduced, size of the silver reduced means when you take the nanomaterials of silver. When you take nano silver, say for example, you have taken 10 atoms of silver, then it is a nanoparticle. You have taken 50 atoms of silver, then it is a nanoparticle. If you have taken 150 atom of silver, then it is a nanoparticle. But if you have taken the Avogadro number of silver, then it will be a bulk material. So size of the silver, size decreasing means, it doesn't mean that you are decreasing the atomic size of the silver. It is not. You cannot decrease the atomic size of the silver. It is that size of the silver decreasing is that the size compared to bulk material. Size compared to bulk material. So if these are nanoparticles, you see here that if you take, say for example, 100 atoms of silver, then the color will be, say for example, this. If you take 150 atoms of silver, then its color will be like that. If you take, say 200 atoms of silver, then the color will be like that. But if you take Avogadro number of silver, the color will be silvery. Now, no color here. You'll see no color is silvery. So this is the different property difference in we told you the different properties at a very small scale. It is showing different property in very small scale. Now, another thing, you see, another property. This is the melting temperature, and this inside it is particle diameter. And we are taking gold. You see, here, the particle diameter is about, say, for example, 30 nanometer, the diameter of particle. It is not the diameter of gold atom. Mind it, it is not the diameter of gold atom. Particle diameter means you have taken, say, for example, 100 gold atoms, and the diameter of 100 gold atoms is that particle diameter. Okay. Now, say, for example, if the particle diameter is, say, for example, 30 nanometer, then its melting point is 1000 degrees centigrade, for example. Now, if the particle diameter becomes 5 nanometer, you see, if the particle diameter becomes 5 nanometer, then its melting point is about 700. Melting point becomes lower. Now, if you take but the particle diameter is about, say, for example, 3 or 2 nanometer, then its melting point is 400 degrees centigrade. And and at one time it will come to 0. So so you see, the melting point of gold, actually the melting point of gold is very high. The melting point of gold is very high, but if you decrease the particle size, its melting point is decreasing. That is the different property in nanoscale. Say, for example, you have taken some gold atoms which have a diameter of 3 nanometer. Then your the melting point of gold is 500 degrees centigrade. So these are the different properties. These are the different properties in the nanoparticles. Now, the basic question is why this is happening? Why this is happening? Why might properties of materials of structure be different at nanoscale? It is yellow in the bulk material, but it is going to red when it is going to nanoscale. Why? Why their melting and boiling points are becoming lower? Two main reasons are there. First one is ratio of surface area to volume of a structure increases. Now, what do you mean by surface area? Surface area means the atoms in the surface, the number of atoms in crude oil, the number of atoms in the surface is known as surface area. Now, for example, if I draw a say, for example, this is a material, and this is a bulk material. Say, for example, this is a bulk material. No fill is better. This is a bulk material. So what will be its surface area? Surface area is the this into this. That means you can say the number of atoms here and number of atoms here. If you multiply, if you multiply this, or if you add the number of atoms in this surface, number of atoms in this surface, number of atoms in this surface above and below, then you will get the surface area. And say for example, there are 100 atoms in the surface. For example, in practice, it will be more than that, lots more than that. Say for example, there are 100 atoms in the surface. Now, if you divide this, say for example, in four, say for example, you have divided it into four portions. So what will happen? What will you see? You see that you are getting a surface here. You are getting a surface here. You are getting a surface here. And you are getting a surface here. Because you have divided, you have, say for example, it is a cake. Say for example, it is a cake. You have cut it here and you have cut it here. Now you are getting more and more surfaces. You are getting one surface here. You are getting one surface here. And also you are getting one surface here, you are getting another surface here, you are getting another surface here, here, here. You are getting more surfaces. And you are getting more surface atoms also. There will be, say for example, if it is undivided, there is 100 surface atoms. But if you divide it means you have cut it. If you have cut it, the same volume, you will get, say for example, 1,000 surface atoms. So the number of surface atom increases. So if the number of surface atom increases, what will happen? The atoms, which atom will go into the reaction? The surface atom first will go to the reaction. If you do one reaction, which atom will go to the reaction? The surface atoms will go to the reaction. Now, if it is undivided, then 100 atoms will go into the reaction. But if it is divided, then 1,000 atoms will go to the reaction. So the property will be different. The property will be different. It is a bulk material, and if you divide it into the nano scale, if you divide it into the nano scale, very small nano scale, if you divide it very small nano scale, then say for example, if you divide it with a very small nano scale, very small squares, if you divide it very small squares like that, then you will get lakhs of surface atoms, crores of surface atoms, which will go into the reaction. But the atoms interior to the interior atoms, that means the atoms which are not in the surface, the atoms in interior atoms will not go to the reaction because it is not exposed. So say for example, you have dissolved the disprene, Have you dissolved discipline in water? Something, say for example, a lump of sugar, say for example, misri. You want to dissolve misri in a glass of water. It will require about half an hour to mix it. But if you hammer it and make it dust and want to dissolve it, it can be dissolved in 3 minutes or 2 minutes. Why? Because surface area increases. So when it goes to nano, say for example, this whole one is bulk and this one is nano. When it goes to nano, the surface area to volume increases. What will call the ratio of surface area to volume of a structure increases because volume is same, but surface area is increasing. Surface area is increasing means surface number of surface atom is increasing. So here you see most atoms are at or near the surface, which make them more weakly bonded and more reactive. And another thing, you see, the surface atom is weakly bonded. Why they are weakly bonded? Because if it is in interior, say for example, this is an atom, this is in the interior of the atom, say it will be bonded strongly. Why it will be bonded strongly? It will be bonded by this way, 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 by this way. In every corner it will be bonded. But if it is in surface, it is bonded in this side, and in this side, but it is not bonded in this side. It is open in one side. So the surface atoms are weakly bonded. They will go into the reaction very fast. So the ratio of surface area to volume of a structure is very much important. Is very much important, and for that the nanomaterial works differently or shows different properties. Say for example, the above your example. What happened? Why this material is decreasing melting point? If you what is the melting point? Say for example, the melting point is the uh, mm, is the is the temperature is the temperature to sorry best I want to make a gold. So say for example, this is a gold bulk material. say for example, this is a gold bulk material, for example. Now, if you want to, what is the melting point? The melting point is the temperature, is the energy that will make this atom and this atom apart from each other. That is the melting point. That is the melting point. Now, to make this atom and this atom apart from each other, uh, what uh, in the gold atom, what I have to do, I have to say, for example, this gold atom, I have to break a lot of bonds to bring it outside. I have to break a lot of bonds because it is bonded with this, with this, with this, with this, with this, and inside this. But if it is like that, say for example, if I, sorry, if it is like that, say for example, this is a gold nanoparticle, I have to break only 2 bonds. And here I have to break 6 to 8 bonds. And here I have to break only 2 bonds. So here it will melt very easily than that. For that, if we reduce the particle diameter, the melting point decreases because a less number of bond I have to break. You require only small amount of energy to make them apart. But in a bulk material, say for example, if it has a number of gold atoms, here you see it has a number of gold atoms. If it has a number of gold atoms, you have to break many bonds to bring them apart. But if there are 3 to 4 bonds, then you have to break 2 to 3 bonds to bring them apart. For that, your the melting point of gold decreases. So, which make them more weakly bonded and more reactive. And you see here, this is weakly bonded. Why weakly bonded? There is no bond at the below or at above. But if you see this atom, it has bond side, below, above, in all direction. It has bond in all direction, and it is strongly bonded. But the surface, these surface atoms are also weakly bonded because they are not bonded in one direction. And they have a lot of surface energy, actually. You have, I think you have, do you have any course on surface chemistry in physical chemistry?
Yes, sir.
No.
Fourth year is chilo, sir. Surface phenomena.
Surface phenomena. This is the surface phenomena. You have surface energy and you have surface, many surface things. But why here it is the bond in which make them weakly bonded and more reactive. So in a nanomaterial, you will get more surface. You will get the surface area to volume ratio high. That means you will get more surface atoms. More surface atom. Say, for example, in this nanoparticle, all are surface atoms. You see here, it is a nanoparticle, all are surface atoms. The diameter of this nanoparticle is about 1 nanometer. For example, it is 1 nanometer because it has 3 atoms, 3 gold atoms. It has a diameter of 1 nanometer. In this nanoparticle, you will find all the atoms are surface atom. So every atom will go into the reaction. But here you see there are there is a 3 surface atom, here 3 surface atoms, here 4 surface atom, but this atom will not go to the reaction because it is an interior atom. So this atom will not go into the reaction, but here all atom will go to the reaction. So going to nano, if you go to downwards, if you decrease the size, then the particle becomes more reactive. Most atoms are near the surface, which makes them more weakly bonded and more reactive. This is the first reason. This is the first reason. And the second reason is quantum mechanical effects are important. What is the quantum mechanical effect? Now, what is quantum mechanics? What is quantum mechanics? Quantum mechanics means, quantum means 1 by 1. There is no fraction between 1 and 2. Say, for example, you are say, for example, you are going through a staircase, Huh? So you have first stair, and then you have second stair. Nothing in between. You don't have 1.5, you don't have 1.6, you don't have 1.7. It is not continuous. Quantum means 1, 2, 3, 4, 5. So how it is 1, 2, 3, 4, 5? Say, for example, a glass of water. Say, for example, a glass of water. You cannot count 1, 2, 3, 4, 5 in the glass of water because it is continuous. A glass of water, you can flow it, you can drink it. It is continuous. It is continuous. You cannot count 1, 2, 3, 4, 5. But when you go to the nanoscale, say, for example, nano water. Nano water means, say, for example, water atoms, water with the length of 10 nanometers. Then you will find 3 to 4 water atoms. That is not continuous. That you can count that there is 1, 2, 3, 4, 5 water atoms, or sorry, water molecules. Then you can count 1, 2, 3, 4, 5 water molecules in nano. But in the bulk state, you cannot count water molecules. You tell that give me a glass of water. You cannot tell that give me an Avogadro number of water, because this is a continuous thing. So in the bulk material, most of the thing in the bulk are continuous, but that not in the quantum state. That not in the quantum state. Quantum state means where you can count them. There is nothing in between 1 and 2, 1 water molecule and 2 water molecule. But in the bulk state, there is something in between 1 and 2. You can tell, give me half glass of water, give me 1/4 glass of water. It is not continuous. Give me 1/4 glass of water. Give me 1/8 glass of water. So it is not it is continuous, but in nanoscale you cannot tell that give me half molecule of water, because in nano, say for example in a 10 nanometer water molecule, you'll get, say for example, 5 water molecules. Here you have to tell that give me 1 water molecule, or give me 5 water molecule, or give me 10 water molecule. That is quantum. That is quantum. So when you are going to small, then you can count them by 1, 2, 3, 4, 5. There is nothing in between 1 and 2. There is nothing in between 1 and 2, 1 molecule and 2 molecule. But when you go to the bulk state, there is something between 1 and 2. Say, for example, 1 glass of water, half glass of water, 1/4 glass of water. There is something between 1 and 2. So this is the difference between bulk and quantum. In quantum state, there is nothing between 1 and 2. Now, what is the effect? What tell is quantum mechanical effect are important. How it is important? Say, for example, I have to draw something. Say, for example, if I can say, for example, this is the valence band, and another one is conduction band. This is the conduction band, for example. This is valence band and this is conduction band. What will happen? In case of semiconductor, there is a gap between valence band and conduction band, which we call band gap. Excuse me, just a minute. Excuse me. Oh, sorry. Say, for example, this is the valence band and this is the conduction band, and this is the band gap. For semiconductor, you know, this band gap is small, and say for metal, this band gap is like that. For metal, there is no band gap. Electron can go from valence band to conduction band easily, and for insulator, there is a large band gap. Electron cannot go from valence band to conduction band. Now, this is the theory we have seen in the electrical properties of the material. You have seen the optical properties of the material. This is the theory of semiconductors. Now, how this band occurred? How this band occurred? If you have two molecules of hydrogen, you cannot find a band, because you'll have, say for example, this is the This is the lower energy and this is the higher energy. You will not find any band here. So why band comes? Because if you have n number of atoms, say for example in sodium metal, in a lump of sodium metal, in a lump of copper metal, in some copper metal, you have n number of copper atoms. So there will be n number of this lower state and this n number of this higher state. So this n number of lower states make a band. That means here you have n number of atoms, n number of these lines. Here you have n number of these lines that are so close together, you cannot differentiate them. So it becomes a band. Here also you have n number of these lines. They are so close that you cannot differentiate. So it makes a band. The lower band is known as valence band, and the higher band is, the conduction band. So what is that? Here you have n number of atoms in the bulk material. But in the nanomaterial, say for example, you have 50 atoms. Now, what will be the size of that atom? What will be the size of that atom? Say for example, this is the band gap. This is the band gap. This is the band gap. Say this is the band gap, and say for example, the value is your 1.8 electron volt. For example, the band gap is 1.8 electron volt for a semiconductor. Now we are decreasing the size. We are traveling to nano. That means, say for example, we have taken 50 atoms. So previously, now you see here there are n number of atoms. So there are n number of lines here. Now we have 50 atoms. So there should be 50 lines. There should be 50 lines. So the bandwidth will be smaller because here it is 6 into 10 to the power 3 lines. So the width is larger. If it will for 50 lines, so the band will be smaller. The band will be smaller like that. The band is smaller. This is for 50 atoms. And this is in case of a conduction band also, because of 50 atoms. So now you will see the band gap. It is increasing. You'll see the band gap. Previously, it was 1.8 electron volt. Now the band gap is about, say, for example, 3 electron volt. 3 electron volt. Previously it was like that. Previously it was like that. So it is 1.8 electron volt. Now the width of the band, not the band gap. What is changing? The width of the band changing. Why would the band changing? Because the number of line is decreasing. Only 50 in place of n number of atoms. 6 into 10 to the power 3. So it will be like that. It will be like that. It will be like this. and your band gap is increasing. So same material, at first it was the band gap was 1.8 electron volt. That means if you supply energy 1.8 electron volt, then an electron from valence band will go to the conduction band. Now, now what will happen if it is a nanoparticle? There are, say for example, there are 50 atoms, then its band gap becomes 3 electron volt of the same atom. Say for example, the atom is gold. In the bulk material, you will find the band gap is 1.8 electron volt. But when it comes to nano, then its band gap becomes 3 electron volt. So the optical property must differ. Say, for example, lights of the visible region in the bulk material, it will absorb 1.8 electron volt and it will go to the conduction band. When it will come from conduction band to valence band, it will radiate the wave of 1.8 electron volt energy, and you will see it as yellow, for example. Now, in the nanoparticle of gold, it will absorb the energy of 3 electron volt. So it will radiate the energy when the electron will come from the conduction band to valence band, it will radiate energy of 3 electron volt, and you will find another color, not the yellow. If you have 100 nanometer of gold, say for example, if you have 300 atoms of gold, then what will be the band gap? The band gap will be slightly smaller. The band width becomes slightly higher. Then the band gap is smaller. It is now 2.9. Then you will find another color. So this is called the quantum effect. Quantum effect means when you are traveling towards the nano, when you are going to the nano, when you are counting the atoms, then your property is changing. When you are counting the atoms, you are counting, say, 200 atoms, you are counting 300 atoms, you are counting 500 atoms. Now their property is changing because the bandwidth is changing. That is called quantum effect. That is called quantum effect. Now you can explain this phenomena. You can explain this phenomena. Why the color of gold is red? Why the color of gold is this much green? Why the color of silver is blue? And why the color of silver is yellow? And why the color of silver is red? You can now explain the phenomena. Because you see here the size of silver atoms are 40 nanometer. Here it is 100 nanometer, and sphere color reflected is like that, and it is like 100 or something. uh, it will be blue. So if the size decreases, or if the size differs, in nanoscale, your your color will also differ, and this is called quantum mechanical effect. It is very important. This is called quantum mechanical effect. Size of a structure on the same scale as the wavelengths of electron, quantum confinement occurs, resulting in changes in the electronic and optical properties. Now, what is quantum confinement? It is called quantum confinement occurs. What is quantum confinement? Say this is the another slide. What happens as particle size becomes very small, 1 to 100 nanometer? Unusual properties of at nanomaterial size, electrons are confined. That is called quantum confinement. Now, what is electrons are confined? Oh, another thing I have forgotten to tell you. Say for example, this is metal. So for metal, what will happen? This will be like that. There is no band gap. That I can bring it here. I can bring it here. So there is no band gap. In metal, it is electron can grow from here to here easily because without accepting energy, is because there is no band gap. Now, what will happen in the nanoscale? What will happen in the nanoscale? So in the nanoscale, the bandwidth is reduced. In the nanoscale, the bandwidth is reduced here, and the band is reduced here. So you're getting a band gap. So the metallic property will not be there. The metallic property will not be there. You are finding a band gap. It becomes a non-metal. It becomes like a semiconductor. Metals become semiconductor or even insulator. So this is the effect of quantum confinement. Quantum mechanical effect. Now, what is quantum confinement? I'm telling you. First, you see electrons are confined, large surface to volume ratio of atoms, more disordered dipoles. What is more disordered dipoles? When this is the bulk material. This is the bulk material. Here the dipoles are like that. This is your ferromagnetic material. The dipoles are in the same directions. So it is, we call it ferromagnetic material. This is the bulk material. But when it becomes nano, when it goes to the surface, there is a large amount of surface energy. So it becomes like that. So magnetic property is changing because surface properties dominate. So magnetic property also changes. Now, what is quantum confinement? Quantum confinement. In a three-dimensional normal bulk material, you have n number of atoms. You have n number of atoms. Say, for example, you have n number of atoms here, and the electrons can grow from anywhere to anywhere because it is a band. It is a band. There is actually no difference in the energy levels here. It becomes a band, and electron can grow from anywhere to anywhere. Now, if it becomes like that, if it is like that, say it is very small. So electron can grow on this side only. It cannot go on this side. It cannot move on this side because this side is nano. Nano means it is very small. It cannot move on this side. It can move on this side only. That is called quantum confinement. You are confining